Just another example of adding fractional expressions. We have somewhat more complicated expressions here. Just as with numerical fractions, we want to express everything in completely factored form. So we're going to express this first term as x plus 4 with denominator x plus 4 times x plus 1. And if you multiply this out using the distributive law, this is what you'll get. This is going to be equal to this. And here we have 2x minus 4 over x plus 4 times x plus 2. And in keeping with the idea that everything should be expressed in completely factored form, I noticed when I was writing this down in the numerator that this clearly factors. Wasn't really thinking about that, but we're going to do that. Okay, so now what do we have? Okay, we have two fractions with different denominators. Now the x plus 4 is common to both denominators, but the x plus 1 and x plus 2 aren't. So we're going to want the common denominator excuse me, to be x plus 4 times x plus 1 times x plus 2. And we accomplish that by first writing down this term and multiplying it by x plus 2 over x plus 2. When we multiply this out, the denominator is then going to be the common denominator, and multiplying by a quantity divided by itself is not going to change the value of the term. So we'll have a completely equivalent term. Okay, so then we have the 2 times x minus 2 divided by x plus 4 times x plus 2. And we're going to have to multiply that by x plus 1 over x plus 1. As you might suspect, this is going to get a little bit messy, but it's really not going to be too bad. So we have then x plus 2 times x plus 2 over x plus 4 times x plus 1 times x plus 2 plus 2 times the quantity x minus 2 times the quantity x plus 1 over x plus 4 times x plus 2 times x plus 1. And then we can use the distributive law. I'm not going to write out all the steps of using the distributive law, but this is going to be x times x plus 2 times x plus 2. And this is going to be 2 times the quantity, well, we could say 2 times the quantity, x times x plus 1 minus 2 times x plus 1 quantity, and go from there step by step with the distributive law, which, given that most people don't understand the distributive law very well and don't apply it as appropriate, I want you to write it out, okay? In any case, what you're going to get here is then, in the numerator, you're going to get x squared plus 4x plus 4 plus, now multiplying all this out, and I'd use the distributive law on these two terms first, leaving the 2 out, and then multiply through by 2. And we're going to get 2x squared minus 2x minus 4. Okay, this is from the first numerator. This is from the second. And that's going to be over x plus 4 times x plus 2 times x plus 1. Now you might ask, well, why don't I multiply these out? Eventually I might. But when I combine these terms, I might get something that factors, and then I'm going to want to compare those factors to these factors. So I want to keep these factors there so I can use them if I need to. Now anyhow, I get 3x squared plus 2x, and I got a plus 4 and a minus 4, so that's all I get. Over x plus 4 times x plus 2 times x plus 1. And then I can factor an x out of the numerator, get x times 3x plus 2 over x plus 4 times x plus 2 times x plus 1. Okay, there is the completely factored form of the sum of these two terms. Now, if I want to go back to polynomial form, I can now return the numerator to the form 3x squared plus 2x, and I can do this product here. I'm not going to do that because it's straightforward. If you use the distributive law, you can do it. And the factored form gives you more insight into this rational expression. Before you could graph this rational expression, you would want to have it in factored form anyway. So I'm going to say that factored form rather than polynomial over polynomial form would be the preferable form. You might not know all the terms I just used, rational function, polynomial, and so forth, although coming into a pre-calculus course, you should be familiar with those terms, but it might have been a while. So we'll define those when we actually get to using them. But anyhow, right there is the application of the principles of addition of fractions to a couple of rational fractions involving rational expressions.